All right, today we are jumping into one of the most important ideas in all of science, the mole. You've probably heard of it, but what is it really? Well, it's this incredible, elegant bridge that connects the world we can actually see and touch with the crazy, invisible, bustling world of atoms. I mean, just stop and think about that for a second. The entire planet buried under 3 miles of marbles. It's an absurd image, right? So that brings us to the real question we're tackling today. Why in the world would scientists need a number so fantastically mind-bogglingly huge? And that question, that gets right to the core of the problem. You see, physicists and chemists live in this kind of paradox. All their theories, all their math, it's all built on the behavior of single atoms. But in the real world, in the lab, they're working with stuff they can actually hold, pour, and weigh. So you've got these two completely different worlds. On one side, you have the microscopic realm, single atoms, invisible particles, numbers so big you can't even count them. And on the other side, you have our world, the macroscopic world of lab scales, beakers, and kilograms. To do any real science, you've got to have a bridge to get from one side to the other. And that bridge has a name, the mole. Now, the very first thing you need to get straight is that a mole is not some fuzzy creature, and it's not a unit of weight. A mole is just a word for a number. That's it. In the exact same way that a dozen is just a word we use for the number 12, a mole is a word for a number. It's just a much bigger one. Think of it as the chemist's dozen. And here is that number, 602 sextillion, 200 quintillion, or as we scientists prefer to write it, 6.022 times 10 to the 23rd. This is Avogadro's number. It is an almost comically huge quantity. So, what's the point? Well, here's where the magic happens. A single atom of silicon is so light it's basically weightless to us. But, and this is the beautiful part, if you get exactly 1 mole of them together, that colossal crowd of 6.022 times 10 to the 23rd atoms, suddenly they have a combined mass you can actually measure on a scale, about 28 grams. Just like that, the invisible becomes tangible. Okay, this brings us to a really important point, and it's a mistake that trips up so many people when they're first learning this. It is so tempting to think of a mole as just another word for mass or weight. But that's just not right. A mole is always and only a unit of amount. It's a count of how many things you have. It's not the weight itself, but it's the brilliant invention that lets us use weight as a shortcut to figure out that count. It's a counting tool. And the secret to doing this little trick is something called molar mass. Every single element has one. It's simply the mass, in grams, of exactly 1 mole of its atoms. This number, which you can find right on any periodic table, is the magic translation key that connects the two worlds. So where does this molar mass number even come from? It's not just pulled out of thin air. You see, in nature, atoms of the same element often have slightly different masses. We call these isotopes. So for something like chlorine, most of it is chlorine-35, but a good chunk is a little heavier, chlorine-37. The molar mass on the periodic table is just a weighted average that reflects how common each isotope is in the real world. And all of this leads us to these two simple but incredibly powerful equations. This is how we put the mole to work. If you've got a pile of something and you weigh it, you just take that mass and divide it by its molar mass. And bam, you know exactly how many moles you have. And once you know the moles, just multiply by Avogadro's number, and you know the literal, staggering count of individual atoms in your hand. This is how we count the uncountable. Okay, so that's cool for counting atoms in a solid, but let's see how this concept lets us build something even bigger and jump into the world of thermodynamics. You've probably seen the ideal gas law, PV equals nRT. It's one of the most famous equations in all of physics, and it perfectly describes how gases behave. I like to call it the constitution for the democracy of particles. And the most important part of that law is right there, that little n for moles. See, the equation doesn't care one bit if the gas particles are huge and heavy like xenon, or tiny and light like helium. All that matters is n, how many moles of particles you have crammed into that container. In this democracy, every single particle gets one vote on the pressure, no matter how big or small it is. And this has some really amazing consequences. Let's say you take 1 kilogram of helium and 1 kilogram of xenon. Because helium atoms are so much lighter, you're going to have way more of them, a much larger number of moles. Now, if you let both of those gases expand and do some work, like pushing a piston, the helium, the gas with the bigger crowd, is going to win by a landslide. It's all about the size of the crowd. not the size of the individuals in it. Now for the final piece of the puzzle, this beautiful connection. Let's zoom all the way back down to that microscopic world. At the particle level, we know what temperature really is. It's just a measure of the average kinetic energy of all those individual atoms bouncing around. It's a single particle property. But back here in our world, in the lab, we can't measure the energy of one atom. Instead, we measure something called molar heat capacity. That's the amount of energy it takes to raise the temperature of 1 mole of a substance by 1 degree. Did you catch that word again? Mole? It's always there, connecting things. And here it is, the grand finale. The big R in the ideal gas law, the universal gas constant, it isn't just some random number scientists made up. It is literally the Boltzmann constant, Kb, which is a tiny number that describes the energy of a single particle, multiplied by Avogadro's number. So the mole, Avogadro's number, isn't just a bridge. It is the exact conversion factor that lets you scale up the physics of one single atom and use it to perfectly predict the behavior of trillions upon trillions of them. It's incredible. So what's the big takeaway here? The mole is this ingenious bridge that lets us count invisible things by weighing things we can see. It teaches us a fundamental lesson about the universe, that very often what matters is just how many particles you have, not what kind they are. And most profoundly, it's the fundamental mathematical link that proves the weird quantum world of a single particle and the classical world we live in are really just two sides of the same coin. It's just an astonishingly beautiful and simple idea, right? One number that seamlessly translates between two completely different scales of reality. It really makes you wonder, what other simple, powerful bridges like this are just hiding out there in plain sight, waiting for us to find them and connect the dots of our universe?